It's a pleasure to announce our next speaker, the Professor Jethro van Ekeren from Universidade Federal Fluminense. I'm sorry if I didn't pronounce your name correctly.
That's no problem.
He works with representation theory of infinity-dimensional Lie algebras, vertex and chiral algebras, and modular forms. Today, he will talk about Nilpotent Slodowy slices and W-algebras. Feel free to start. Thank you.
Okay, great. Yeah, well, thanks very much for the introduction, and I'd like to thank the organizers for giving me the opportunity to speak here today. So today I'd like to talk about some joint work with Tomoyuki Arakawa and Anne Moreau. So basically, the overarching goal is to better understand a certain class of vertex algebras that are called W-algebras. So I'll say a little more about what W-algebras are later in the talk. But this is a class of algebras that have a number of applications in representation theory. They appear in the geometric Langlands program, and they appear in connection with quantum integrable systems and statistical mechanics and things like that. And also finite analogues of W-algebras are relevant in the study of unitary representations of Lie groups. So there are a number of reasons to be interested in W-algebras. The problem is that they're relatively difficult to construct and have complicated structures. They're difficult to understand. And so the more immediate goal of this work that I'm going to describe is to relate these W-algebras, which are difficult, to an easier class of vertex algebras known as the affine vertex algebras. And one should think of these as being relatively easier to understand. And so the very first step is to discover which W-algebras are in fact isomorphic to some affine vertex algebra. Or slightly more generally, to see if we can find some large affine subalgebra in a W-algebra and use that as a starting point to better understand the structure of the W-algebra. Okay, so to get started, let's take G to be a simple Lie algebra with the complex numbers. We take a non-degenerate invariant bilinear form, use this to construct the corresponding affine Lie algebra, G hat. So this is G tensored with Laurent polynomials in one variable, summed with a central term. The Lie brackets are given explicitly by these relations here, and you see that K is indeed central, commutes with everything. And I'd also like to talk about modules over the affine Lie algebra. So for this, I'll introduce G hat plus. This is, in a sense, the positive half of the algebra. So this is GT plus the central element sitting inside G hat. And if we fix a parameter, a value of a parameter K called the level, it's just some complex number, then we can use it to construct so-called vacuum module. So to do this, we start with a single vector, Vk, and we let Gt act trivially on this and let the central element act by a parameter K, the level. And then we induce to the whole algebra, and we denote this by Vkg. And we're also interested in the irreducible quotient of this vacuum module. We'll call this Lkg. Okay, so I thought it'd be nice to begin to try and give a mental image of these modules. So here's the vacuum module for SL2. And you can see I've put Vk up here at the top, and then going down one step, I've f minus 1, h minus 1, e minus 1 applied to this top vector, and so on and so forth. I apply f minus 1 2 times, and so forth. You'll notice I've put f minus 2 down here 2 steps below Vk. So implicitly what I'm doing here is introducing a z plus gradation in this module, right? And all the graded pieces have are a finite dimension. This grading descends to the irreducible quotient, Now, the structure of the irreducible quotient depends a lot on the specific choice of level. So here I've drawn it for k equals 1. And this is so you'll notice that the set of weights in this module has gone from this pyramidal shape, in the case of the vacuum module, to this parabolic form. This is a general feature of the irreducible quotient at positive integer levels, such as this. You'll see that the multiplicities of the weight spaces look quite interesting. And in fact, this motivates us to introduce the so-called partition function of any one of these modules. So this is just, as you see here, a generating function for the dimensions of the graded pieces. And although this is a formal power series, I've written this as a function of tau here because on the next slide, I'm going to want to consider these series as functions of this complex variable tau, which lies in the upper half plane. And here I've set q. I've identified q with e to the 2 pi I tau. And in this specific case, L1, SL2, this does indeed converge because, in fact, we have an explicit formula for the character, for the partition function, coming from representation theory. And if you wanted, you could use this formula, put it into Mathematica, and determine the dimensions of the graded pieces to any desired order. But the interesting thing about these partition functions is that they're modular after being subjected to a small correction or normalization. In this particular case, one has to multiply by this funny factor, q to the minus 1 over 24. Just to recall briefly, a modular function means, so it's a holomorphic function on the upper half complex plane that should be invariant under the group generated by two transformations, which are written here, denoted by T and S. So in fact, these generate an action of the group SL2Z. And then this normalized partition function, for L1 SL2, is actually something slightly weaker than what I just described. It's not really a modular function in that sense, but it's something called a vector-valued modular function, which basically means that it's an element of a finite dimensional vector space, which is invariant under this action that I've just described. And in fact, this is a general property of positive integer levels. So G can be an arbitrary simple Lie algebra, and if K is a positive integer level, then the corresponding partition function is also a vector-valued modular function. So one explanation for this comes from the Weil-Katz's character formula. So this formula expresses these partition functions as quotients of theta functions. Theta functions are modular, and so therefore are the partition functions. So in general, for more general levels, or for arbitrary level, this modularity does not hold necessarily, but there is one more general class of level for which it does hold. These are called admissible levels. These were introduced by Katz and Wakimoto. So I don't really have time to go deeply into the background on admissible levels, but basically there's certain rational levels which are characterized by these conditions here. So minus Joule-Coxeter number plus some fraction p over q and some conditions on p and q, which have this important property of modularity, or rather the partition function is modular for these levels. So just for later reference, I want to introduce these words. The principal admissible and co-principal admissible refer to these two cases. In other words, they refer to whether the denominator of the level is co-prime to the lacing number of the Lie algebra or not. This distinction turns out to be important because certain important root subsystem that will appear in these respective cases turns out either to be an untwisted affine root system or a twisted affine root system. But anyway, so an important implication of modularity is this result on the asymptotic behavior of the partition function. So if we take one of these modules LKG, which is modular, and let the argument tend to 0 along the positive imaginary axis, then asymptotically the function behaves as follows. It's some constant times exponential of a constant over t. And these coefficients, g and a, that we can extract are called the asymptotic growth and asymptotic dimension of the module. And they're quite important because, well, in this theory, essentially all of these modules are infinite dimensional. So the dimension is not an interesting invariant. But these coefficients, g and a, which one can extract, non-trivial invariants that serve in some sense like a dimension. And this asymptotic is proved using the modularity. So basically what happens is the S transformation relates the limit as t goes to 0 with another limit as t goes to infinity. But when t goes to infinity, that corresponds to this other parameter q going to 0. And the dominant term is then just the leading term in the Q series expansion. And since this is, so this is easy to understand explicitly, and then can be used via modularity to understand the asymptotics. So to give a precise statement, Katz and Wakimoto in 1989 proved, it gave explicit formulas for the asymptotic growth and asymptotic dimension in the case of principal admissible levels. So here they really used the fact that the root subsystem that I mentioned before was isomorphic to an untwisted affine root system. So yeah, you see I have some formulas for G and A in terms of the data of the level, P and Q, and also basic data associated with the Lie algebra G. So the first new result in this talk is the following. So we prove, we find similar formulas in the co-principal case. So you see the relatively similar formulas. And so there's no essentially new idea in this. We basically do the same calculation that Katz and Wakimoto did, but there are several points at which things become more complicated because of the appearance of these twisted affine root systems. And so one can see an interesting feature of these formulas is that in this co-principal case, whereas previously the Joule-Coxeter number of G, the Lie algebra G, had appeared, now what appears is the Joule-Coxeter number of the Langlands Joule of G. And this is the, well, sort of a tip of an iceberg in a sense. It's related to these connections that I previously mentioned of this material with the geometric Langlands correspondence, which is a correspondence that relates objects associated with the Lie group and its Langlands Joule. So anyway, we have these formulas that we'll use later. Yeah, so I had said that the objective here is to understand W-algebras. In order to explain what they are, I have to say what vertex algebras are. So indeed, these modules, VKG and LKG, are examples of vertex algebras, which in general are certain graded vector spaces that come equipped with an infinite number of products. And these products that I write A, N, B have to interact, satisfy some axioms. In order to describe the axioms, it's best to gather all of the products together into a generating function, in a, as I've written here, this y of az. And now these functions, y of az, for different values of a and b, essentially have to commute in this weak sense, given by this axiom here. Now, interesting. So one can associate many invariants to vertex algebras. So one is the following structure. So if we take the subspace of V, a vertex algebra spanned by all -2 products, and consider the quotient, then the -1 product descends to that quotient and turns it into a commutative algebra. And then furthermore, the 0 product turns it into a Poisson algebra. So we have a Poisson algebra associated to any vertex algebra. And we'll denote by XV the spectrum of this and call it the associated variety. So this is a Poisson variety. So for example, the associated variety of the vacuum module is associated with G is just G star, which is a well-known sort of first example of a Poisson variety, right, with the so-called Kirillov constant Souriau Poisson structure, which just comes from the Lie bracket in G. So other Poisson varieties appear as well. If we look at G under the action of the adjoint group, then it breaks up into so-called adjoint orbits. And these are all symplectic varieties inside G. And of particular interest are the so-called nilpotent cones. This is the set of all nilpotent elements. And this turns out to be a union of finitely many adjoint orbits. So for example, for SLN, a nilpotent element can, as can any element, be put into Jordan canonical form. And then it's completely determined up to equivalence by the sizes of the Jordan blocks. So we can associate to the nilpotent element in this way a partition of N. And this turns out to be a bijection. There's a bijection between the partitions of N and the set of nilpotent orbits in SLN. Similar pattern, but more complicated, holds in other types. So I thought it'd be fun to draw here the set of nilpotent orbits for E7. And so here you can see we have some complicated set of inclusions here. So these lines correspond to this ordering defined by saying that O prime is less than or equal to O if O prime is included in the closure of O. So it's this orbit closure order. And in fact, for SLN, this order on the set of nilpotent orbits corresponds to the dominance order for partitions. So anyway, the relevance of all this, the present case, is my colleague Tom Yuki proved that the associated variety of LKG at admissible level K is always the closure of some nilpotent orbit in G. And this nilpotent orbit, it turns out, depends only on the denominator of the level, in fact, so we can denote it OQ. So just to illustrate this, if we take SLN again, then we can do the Euclidean division of N by Q and get this remainder S. And then this allows us to write a partition, lambda, which is just a bunch of Q's and then the S. And OQ is, in fact, this O lambda. In particular, not every nilpotent orbit occurs as an associated variety. So now finally I can mention about W-algebras. So to construct these, one starts with an admissible affine algebra and fix a nilpotent element. Then one can write down a complicated cohomological complex called the BRST complex. This process, I forgot to write it, is known as Hamiltonian reduction as well, or Drinfeld-Sokolov reduction. Then one takes the zeroth cohomology of this complex, and this again is a vertex algebra, and this is the so-called W-algebra. So it depends on a choice of a Lie algebra G, a level, and nilpotent element. These are most interesting when this element F sits inside the closure of OQ, so let's assume that from now on. And now the associated variety of this vertex algebra is an intersection of two things. So it's the closure of OQ, which depends only on the level that we started with this other variety, SF, that depends only on F. This SF is what's known as the Slodowy slice. So to define it, one embeds F into an SL2 triple, and then SF is just F plus the kernel of the adjoint of E. And indeed, these intersections, SOF, are slightly less well known than the Slodowy slices. So Slodowy slices are abundantly studied in Lie theory and Poisson geometry. These so-called nilpotent Slodowy slices are slightly less well known, but also studied classically. Well, anyway, so characters of these W-algebras, sorry, partition functions of the W-algebras are also modular, and their asymptotics are also known, again by Katsuwakimoto in the principal admissible case, and by us in the co-principal admissible case. But now, finally on this slide, I come to the key technical lemma that allows us to prove something. So let's define G natural to be the centralizer of our SL2 triple in G. So in a certain sense, this G natural survives the Hamiltonian reduction. So more precisely, one has a morphism from the corresponding vacuum module for G natural at some level K natural to the W algebra. And key technical lemma says the following, that one now has the W algebra, we have this other vacuum module, and we consider its irreducible quotient. Both of these have asymptotic data, A and G, asymptotic dimension and asymptotic growth. And if these data coincide, and also some additional technical hypotheses, for example, if this nilpotent element is even, so I didn't want to go too much into detail about the technical hypotheses. If the asymptotic data coincide, basically then we know that the two vertex algebras are isomorphic. And I think I don't really have time to say much about the proof. It's uses some category O theory, multiplicities of irreducible modules inside projective covers. It's a little bit complicated, but the point is, using the result, we can start looking for isomorphisms between W algebras and affine Lie algebras. So the idea is to begin with some nilpotent Slodowy slice, see if it's isomorphic to some nilpotent orbit in the corresponding G natural. If it is, then that suggests that there might be an isomorphism between the corresponding vertex algebras. So we have candidates for isomorphisms. We then compute asymptotic data on both sides. A lot of this we do on the computer. And if they turn out to coincide, then we get isomorphisms. So in this way, we got many kind of sporadic isomorphisms and also a few families of isomorphisms. So here's a random example, E7 at this particular level, minus 35/3. Then one can compute the corresponding nilpotent orbit. Here, Q is 3, the denominator. If F is this particular element in the closure, then it turns out G natural is G2 at a particular level. And by coincidence, the asymptotic data on both sides coincide. And so we conclude that there's an isomorphism. So that was just one example. We were a bit more systematic in general. So we produced, here's a screenshot from the paper. So these are the cases associated with E7. We produced perhaps 100 or so sporadic isomorphisms this way, and also a few families of examples. So here's a case involving SLN and a particular nilpotent orbit, which takes a number of Qs and then a number of 1s. And this W algebra turns out to be isomorphic to an affine algebra for SLS. So here S was this remainder on dividing N by Q. Okay, so yeah, that's all. Thank you very much.
Questions or comments? So let's thank the Professor Jethro again.